people of South Central Texas are fortunate to have a source of high-quality, replenishable water underneath them in the Edwards Aquifer. It's a continuously circulating freshwater system that may be unique in its structure and functioning. To understand how it works, one must understand its origins, its various geological strata, and the way it connects to other underground formations. One can do that best by actually going inside the Edwards Aquifer. First, a definition. An aquifer is a permeable underground rock formation that contains significant amounts of water. The water reaches the surface through natural springs or through wells that have been drilled to tap the underground water. The Edwards Aquifer is about 180 miles long and from 5 to 40 miles wide. It extends from Brackettville at its extreme western edge to Kyle in the east. The underground reservoir covers 3,000 square miles. Geologists have defined 3 separate zones that make up the Edwards Aquifer region. The Artesian zone underlies and supplies water to 6 counties: Kinney, Uvalde, Medina, Bear, Comal, and Hayes. The drainage area of the aquifer, the watersheds where rainwater runs off to streams to replenish or recharge the aquifer, encompasses several additional counties. Rain that falls on the counties of Edwards, Real, Bandera, Kerr, and Kendall flows overland in streams until it reaches the recharge zone, where it disappears into cracks in the stream beds and enters the aquifer. Once water percolates into the aquifer, it generally moves from west to east. There's a divide at either end of the aquifer that separates it from similar regions to the east and west. The Brackettville Divide in Kinney County is an underground water table ridge from which water flows away, just as rainwater flows down a hill on the surface. The Edwards Formation continues past Brackettville, through the city of Del Rio with its abundant San Felipe Springs, across the Rio Grande and on into Mexico. The water-bearing layers there have different names, but they too are aquifers. At the eastern end of the Edwards Aquifer region, the Kyle Divide in Hayes County is also a water table ridge. Groundwater has a difficult time moving up underground ramps, so groundwater south of Kyle funnels back toward the San Marcos area, with much of the water emerging at the San Marcos Springs. On the Austin side of Kyle, groundwater moves northerly in limestone and emerges at Barton Springs, which flows into Austin's Colorado River. The southern border of the aquifer is a boundary called the bad water or saline water line, which separates fresh water within the aquifer from water having a much higher concentration of dissolved minerals. The saline water line is located by a contour line following water containing dissolved solids measuring 1,000 milligrams or greater per liter. Southeast of the saline water line, the aquifer is much less permeable. Here, groundwater moves much slower and stays in contact with the limestone and other minerals longer, which greatly increases its mineral content. This water contains high levels of dissolved calcium and sulfide. The reason it's called bad water is its smell, a pervasive rotten egg odor emanating from hydrogen sulfide gas commonly associated with highly mineralized water. The Edwards Aquifer is known as an Artesian Aquifer because water in it is confined to layers of porous Edwards limestone between the layers of impermeable rock. Underneath the Edwards limestone is Glen Rose limestone. Above it is the Del Rio clay. Both of these confining layers are relatively impermeable because of their high clay content. The water in the Edwards Formation is under pressure, like air in a car's tires. Because of this pressure, some wells flow freely out of the ground and do not need to be pumped. Back in 1891, George Brackenridge, who started the first water company in San Antonio, drilled a well downtown. The water pressure within the aquifer was so great in those days that a geyser of water shot 20 feet into the air. At Fort Sam Houston, an artesian well designated J21 flowed continuously, except for severe droughts, without a pump from the time it was drilled in 1912. In 1991, the Edwards Underground Water District inserted a borehole television camera into this well to look for cracks in the casing. The television images from hundreds of feet down the well revealed corroded conditions, so when engineers determined that the casing was irreparably damaged, this well was permanently plugged to conserve water. Prior to 1991, the most productive well in the Edwards Artesian region, thought to be the most productive artesian well in the entire United States, was a San Antonio City Public Service Board well on Mission Road. Drilled in 1941 to a depth of 998 feet, it flowed more than 18,000 gallons per minute out of a 20-inch bore. The well sent a continuous blast of water straight up out of the ground to a measured height of 40 feet. But even that record was broken in 1991. A well drilled in southwest Bexar County near the Medina River produces more than 23,000 gallons per minute from a 30-inch bore. When the driller punctured the water-bearing Edwards limestone at about 1,200 feet, the surge of water under high confined pressure threw two 80-pound pieces of reaming bit back up the well, along with large rocks. Today, this well is controlled by a valve on the surface to use the water in a commercial fish farm operation. The driller was extremely lucky here in hitting a cavern, where permeability of the aquifer is exceedingly high. That caused the aquifer to yield an enormous flow of water into the wellbore with sufficient force to lift heavy objects. Wells just 100 yards away are not as productive. Many other high-yield wells exist in the immediate vicinity, but this well shows that while all the Edwards Formation is productive, some areas are much more productive than others. Why does the water in the Edwards Aquifer have such pressure? Groundwater in the water table or unconfined area in the recharge zone is at atmospheric pressure. But as the Edwards limestone slants away from the surface underground, the weight of the overburden and the weight of the groundwater itself builds greater and greater pressure in the confined zone. What is called head in hydraulics is the combination of elevation and pressure, and it's a description of how much water exists uphill from the measurement location. Water moves from a higher head to a lower head, that is, from a higher potential energy state to a lower one. But water doesn't necessarily move from a higher pressure area to a lower pressure area. A clarification. In the recharge zone, one may use the term uphill for the water that lies higher or farther north. But in the artesian zone, where the water is confined and under pressure, the terms up dip and down dip are used. An illustration will explain the difference between uphill and up dip. In this side view of the aquifer, the water in this faulted block is actually higher in elevation than the previous block, but it is further away from where the fault began on the surface, and it is therefore down dip. The previous block is up dip from the last. Which path would the aquifer's groundwater usually take? Not from the higher elevation, but rather from the up dip block into the down dip block, because the head is lower in the down dip block. This illustration shows how the average water level in observation wells decreases from the west to the east. It also shows that the level in some wells varies much more than in others. In Uvalde, the observation well has an average variation of only 10 feet from its mean level of 875 feet, because it lies close to the water table. By contrast, the Sabinal observation well has an average level of about 775 feet, but it varied in the last decade in drought from 720 feet to 835 feet in a flood year. The Castroville test well has an average level of about 680 feet. Further east, the San Antonio Index well's average level is 650 feet, but it experienced more than 70 feet of fluctuation in the 1980s. Notice that the New Braunfels well at 625 feet stays almost completely constant in level, and likewise, the San Marcos well at 575 feet varies only a few feet from drought to downpour. These last two wells are nearly constant head because nearby spring flows dampen out most variations. How is the level of the aquifer measured? If water is at, say, this level in the water table uphill, then one would think, since water seeks its own level, that the potential is for the water to rise and open well bores to that level. but there is friction loss over great distances, which reduces the height that water may reach. What's the significance of this? When a news report says, "Today the aquifer is at 650 feet," it doesn't mean that the actual water level is 650 feet throughout the aquifer. What the report is saying is that the water level in a particular observation well has been pushed by hydraulic pressure to that level, 650 feet, which may be hundreds of feet above the top of the Edwards limestone formations. There are approximately 40 observation wells in the Edwards Aquifer region. In San Antonio, the index well is this one, named J17, located on Fort Sam Houston. The land surface here is 730.8 feet above sea level. The Edwards Formation starts 500 feet below ground surface, but the level of water in the well is only 80 feet or so below the ground. The water has risen in the well's casing on this day to 650 feet above sea level, more than 400 feet above the top of the aquifer. The highest water level that has ever been recorded in this well was in June 1992, when the level of this well surpassed 700 feet for the first time. Continuous heavy rains pushed the level up the well bore to a point less than 30 feet below the ground's surface. Rainwater that had recently fallen on the recharge area had made the water table rise slightly, nothing like the rise in the index well. Why did the well's level rise so much more than the level in the water table higher in elevation? That's because in the Artesian area, the release of pressure can only be reflected in small leaks, springs or wells, so water rises higher in the wells in response to the effect of extra pressure in the recharge zone. During extended periods of heavy rainfall, artesian pressure is clearly evident. For example, during the rainy spring and summer of 1992, the San Antonio springs began flowing continuously due to increased artesian pressure from incoming water. These springs, long forgotten by most San Antonio residents, inconvenienced nearby property owners. Within the aquifer, how fast does the water move? The speed of the water flow can vary tremendously, from only a few feet per day to more than 50 feet per day. Compared to surface water, the aquifer's flow rates are relatively slow. But compared to other underground water sources in North America, many of which have flow rates of a few inches per day, the Edwards Aquifer water flow is very fast. Other indicators give evidence to the speed of water flow within the aquifer. Wells that are close to the recharge features, such as sinkholes, sometimes become cloudy and turbid after rains. This shows that rainwater definitely influences the water underground. Wells further away from the recharge zone generally show no increase in the mineral content or suspended solids after rains, which indicates that water movement is faster close to the recharge zone than further away. How does the aquifer's water maintain its purity? It happens in two ways: by settling out solids and by diluting contaminants. Bacteria entering the aquifer dies when it's removed from sunlight and its nutrient source. Then it settles. And the vast amount of water in the aquifer dilutes small sources of contaminants. The circulation of the water in the aquifer reduces the concentration of any pollutant. Despite the aquifer's apparent ability to dilute contaminants in its water, we should not relax our efforts to prevent pollution. The threat of contamination increases as the population grows and development occurs, especially in the area over the recharge zone. There are at least 3 potential sources of pollutants for the Edwards Aquifer. Gasoline and petroleum products can contaminate our water in runoff from parking lots and roads, and from leaking underground storage tanks. Just 1 gallon of gasoline can make nearly 1 million gallons of water unfit for drinking. Another potential source of contamination is nitrogen-based fertilizers and pesticides leaching from farmers' fields and from homeowners' lawns. Fertilizers in our water causes explosive algae growth, which fouls the water. A third pollution source, one of the most dangerous for humans, is contamination from human waste from septic tanks and sewer lines. Over the recharge zone, where many homes are not connected to municipal sewer lines, their toilets and drains are funneled to nearby land, where the wastes can percolate into the aquifer. The rate or speed at which water moves through the aquifer depends on both the water level gradient and the transmissivity. High transmissivity areas can have much greater volumes of water flowing through them in a given period of time than areas of low transmissivity. Transmissivity is a measure of the aquifer's ability to move water through a 1-foot wide column of the aquifer. Transmissivity equals thickness times permeability, or hydraulic conductivity. Permeability is a measure of an aquifer's ability to move water through a square foot section under a gradient of 1 foot to 1 foot. Permeability or conductivity is expressed in number of feet per second, but it is not the same as velocity or flow rate. Water flow rate in the aquifer is determined by Darcy's law, which governs fluid velocity in any structure, even the fluid flow in our bodies. Darcy's law says that velocity equals hydraulic conductivity, or permeability, times the hydraulic gradient, or changes in height, divided by the change in distance. The formula thus reads V equal K times delta H divided by delta L. What Darcy's law tells us is that to get more water through the aquifer, we can vary only one thing, since we can't vary permeability of the limestone or the distance between recharge and discharge. We can only vary the hydraulic gradient. How can that be done? By either increasing recharge or else by extracting more water from the aquifer. In the first instance, the level at one end of the aquifer is raised. In the other, at the other end, the level is dropped. Either way, increasing the gradient and therefore, according to Darcy's law, increasing also the velocity of water movement. The velocity in Darcy's law is actually flux, or the rate of movement through a unit cross-section. To get velocity, one would divide the flux by porosity. An aquifer example will illustrate. Which would have a greater velocity, a given volume of water moving through an underground cavern, or the same volume of water moving through honeycombed limestone? In the cavern, the volume moving through an open space, which has a porosity of 1, has the same velocity as its flux. But in the limestone, which may have a porosity of 10%, to get the same volume of water through the limestone as through the cavern, the velocity would have to be 10 times that of the cavern. So the limestone sample's velocity is greater. In this first section on the Edwards Aquifer, we have discussed its location, its divisions, its boundaries, the concept of Artesian pressure, and some of the terms used to describe water movement. We also looked at how water levels are measured and how water movement is measured. In the next two sections, we will explore more aspects of the Edwards Aquifer, how much water is stored underground in the aquifer, how it is recharged by rainwater, and also how the Edwards Aquifer was formed in geologic time.